Hey, welcome to the class meeting 19 of EECE574, the graduate level probability and random processes. The first announcement is quiz 2. So it will be taken for 2 days from Tuesday, April 30th to Thursday, May 2nd. You will be given approximately 48 hours to finish the quiz. Handout for chapter 5 is updated. Because today we will finish chapter 5 of the, chapter 7 of the textbook, the populist graduate textbook. But I found that some rearrangement of material is necessary. So I've updated and you need to download it again. Handouts for next chapters are uploaded also. And I've decided to use our undergraduate textbook kind of expanded or augmented by the graduate level material because I love the undergraduate textbook after some rearrangement of the materials and modification and augmentation. So we are not going to directly cover the chapter 9 of Populists, but we will mostly follow the sections of Peebles' book, but the materials will be a graduate level. Messages from instructor is the same. You need to fill up your toolbox with fundamental tools, which includes the skill in math, especially in analysis and measure theory and measure theoretic probabilities. And also you need a lot of practice. Without practice, your toolbox is just filled up with tools you cannot use, and no one wants that. So you need a lot of practice. And the researchers have found some necessary conditions for good practices. And you can remember these 3 F. First, you have to focus on what to improve. Second, you need an immediate feedback in the practice. And the third, you need to fix after realizing what is wrong and what can be differently performed. By the way, these days I'm reading a new book related to the good practice, and they say that sometimes you need to intentionally mix different practices so that you can unlearn what you've learned, something like that. I will talk about that later if we have time. So here goes the overview. I've expanded this section. So we covered chapters 1 through 5 of Peebles' textbook, also augmented with graduate level materials. And then we are covering the chapter 7 of the Populist textbook. And then we are going to move to chapter 6 of the Peebles, expanded a lot. I've changed the order a little bit of the sections. First, we will cover the random process concept, stationarity and independence. Then we will study Gaussian and Poisson random processes. And also, most of you are communication engineering graduate students, so we need definitely complex valued, not only random variables and vectors, but also random processes. So we will cover that material. And we will talk about correlation functions and what is the ergodicity and how to measure the correlation functions. And then we move to the chapter 7, we entitled as Random Processes with subtitle Spectral Characteristic. That is one of the most important material related to communication engineers because most of the physical layer communication engineers requires to know what is power spectral density and how to use a measurement device called the spectrum analyzer. So we have a lot to cover, and I hope in this semester, most of the holidays are on Mondays and Wednesdays. So I believe we can reach our 30th class meeting. Anyway, corrections and clarifications, I believe we need clarifications, but anyway, we will cover soon. So just remember, last time in a hasty, I just said that in order to prove weak law of large numbers, you need the the mean square convergence that is half correct and half incorrect, because we not only need the mean square convergence, but also need to use so-called the Chebyshev inequality. And second one is that last time I've shown you in some example, when do we need the convergence in distribution in order to approximate the bit error rate. But some of the titles of my subsections said that we have a DS-CDMA example. Actually, that was not DS-CDMA example. We are going to cover that example today. And it will be interesting to find the differences between last class's example and this class's example. Anyway, here goes the review. We've discussed what is the equality. What does that mean by two random variables are equal? Actually, there are many definitions. Everywhere or sure equality, which is useless in talking about probabilities. So it started from the almost sure or with probability 1 equality. And then we talked about the in distribution equality, which is actually is not equal. Your two random variables may have the same CDF or PDF, but their outputs may be totally different. For example, you may have some random source that generates x1 and x2. And you know that the CDF of x1 equals CDF of x2 for all x real. However, if you plot the dots, so if you plot a two-dimensional scatter plot, then you will be surprised to find that the CDF's equality does not guarantee that you observe some dots on this line, okay? So as you've seen in one of the examples, the simplest one is just generate the uniform random variable u, and you have two branches. x1 equals u, x2 equals 1 minus u. In that case, what happens? Then your two-dimensional scatter plot will exactly look like this. And they are not equal because x is never equal to y except at the origin. And that probability is what? 0, right? So be careful. The equal in distribution of two random variables does not mean this one. So sure implies almost sure, and almost sure implies in distribution, but the converse is not true. Got it? Now we move to the approximate equality of two random variables. And I told you that the most important trick the engineers learned from mathematicians is what? Not whenever, in many cases where you want to approximate something, you construct the sequence of something that converges to the other thing. For example, you want to claim that two random variables x and y are very closely equal. For example, you plotted scatter plot, and then they are almost, right? They are almost lies on this y equals x line, right? With some ignorable error, then you may be sure that, okay, under some condition, we may say that they are almost the same. And what do we do to claim such a thing? We construct a sequence of random variables. And of course, let's say this as sum, and where x with very large parameter equals this random variable, for example. In that case, if you show that this sequence of random variables converges to y in some sense, then what can you say? for example, x very, very large, then 10 to the 6 may be close enough to claim your approximate equality. So we construct a sequence of random variables that converges to the right-hand side and show and claim that the x is close enough to y for our application. And in order to discuss such convergence of a sequence of random variables, we need to remember our convergence of a sequence of functions to a function. There were definitions like uniform convergence, every-year convergence, almost every-year convergence, and convergence in the piecemeal and convergence in measure. However, when we talk about the probabilistic material, we don't need uniform and everywhere convergence. So we have 4 modes of convergence, and 3 of them are same, like almost sure convergence in the piecemeal and in probability measure, simply in probability. The last thing is related to what? This one. Distribution converges. So we have 4 modes or 4 versions, 4 different definitions of convergence of a sequence of random variables. And also, I just presented that almost sure convergence implies in probability and in distribution convergence. And convergence in the piecemeal with p greater than or equal to 1 implies the convergence in measure, probability and convergence in distribution. So whenever you need, for example, convergence in distribution, you may directly prove the convergence in distribution, or you may find it easier to prove convergence in probability or convergence in the piecemeal, especially p equals 2, so that you can use the second order moment, something like that. However, sometimes you really need convergence almost sure or with probability 1. And then in that case, what do we do? That's today's topic. So first thing is to use the strong law of large numbers, but that its applicability is very limited to the arithmetic mean of something. Anyway, that is an important topic. So we learn the strong law of large numbers, just a statement without proof. And then we talk about weak law of large numbers, that is in the category of convergence in probability. And then we move to central limit theorem. And then we talk about Borel-Cantelli lemmas. Got it? And we will talk about how to generate random numbers. And then we will cover sampling and some limit theorems. Again, that section is from the undergraduate book. So a lot of parts will be overlapped. Okay, so here goes the law of large numbers. Whenever you want to remember the law of large numbers and central limit theorem and other things, they are confusing. So I also had a lot of confusion. So here goes the simplest box you want to remember related to any law of large numbers. Law of large numbers is about what? You construct a sequence of random variables where each term of the sequence is what? The arithmetic mean, simple arithmetic mean. What is that? Sum of n random variables divided by n. Of course, in order for these random variables to be summed, what is the most important condition, necessary condition? Their physical units must be the same. Okay, you cannot add 1 gram of apple with your mother's love. You cannot add, right? So their units must be the same. And then the law of large numbers, the collection of theorems actually. So it's like this. Suppose here is the set of all, the theorems or lemmas, let me just say theorems, the theorems, the set of all theorems. The set of all theorems on the convergence of a sequence of random variables. Then, as we've seen, what? Almost sure convergence, blah, blah, blah. But here I present like this, law of large numbers. So there are many theorems inside this subset. Got it? There are many theorems with different conditions. But mostly they can be divided into two. One is the strong law of large numbers. Also, in this subset, we have many theorems. And here we have weak law of large numbers. The reason why we have these two subsets of theorems is that they rely on different convergence mode. In the strong law of large numbers and the weak law of large numbers, we have the same form like this. Arithmetic mean converges to the common mean. And this common mean value are common for the random variables to be summed. So first the condition, of course, it can be different. Okay, in some strong law of large numbers, it says that this is the some theorem just replaces this one as limit n tends to infinity and mu1 plus mu2 blah blah blah. So you may allow different mean values. However, the one of the strong law of large numbers assumes that the arithmetic mean of the means, arithmetic mean of the statistical means converges to something, and then they say that this converges to that. But we are not talking about that. What I want to say is that there are many different versions of the law of large numbers. You have to remember that, okay? Because I find many graduate students just say that there exists only one unique strong law of large numbers. That is not true. Probably even at this moment in the world, there will be a lot of PhD students in statistics who are proving new strong law of large numbers, new weak law of large numbers, new central limit theorems under different conditions. Okay. Anyway, so what I want to say is that there are many strong law of large numbers, but one of the famous strong law of large numbers is assuming that the random variables have the common mean value. And of course, one of the most famous weak law of large numbers also assume that the random variables have the common mean value. Got it? But that commonality of the mean value is not necessary for all law of large numbers. Some law of large numbers has relaxed version. Anyway, this is one of the simplest ones. So we learn these two. So the first law of large numbers is a strong law of large numbers in this condition. They are simply IID with common mean and variance. Be careful. Even though random variables are independent and identically distributed, the statement of IIDness does not guarantee the existence of the common mean. Even the existence of common mean does not guarantee the existence of common variance. So this theorem has very, very strong three statements. First, IID, you may say that is two conditions, but IIDness. Second, existence of the common mean. Third, the existence of the common variance. Got it? And then people have shown that the arithmetic mean, that is the nth term of the sequence you have just constructed, converges to what? The arithmetic mean sequence converges to the mean of the random variables with probability 1, which means that surely, almost surely. So by using P, the PR, the probability, you have to write in this way. The strong law of large numbers says some probability equals 1, right? Because it says converges with probability 1. Probability 1. Now, what event? What event? This is your statement, okay? Of course, this is an abuse because we have this 2, right? And also, we may need something like that. So some people love what? Probability of the event. This is an event. What event? Such that what? Again, I need to use, but first we need this. Right? And then probably you want to replace this limit equals mu x as what? For every epsilon positive, blah, blah, that stuff. Right? Anyway, I'm not going to prove this. It relies on the Borel-Cantelli lemma, if I correctly remember. Second one is the weak law large numbers, where we prove the convergence in probability. What does that mean? That means for every epsilon positive, your sequence of probabilities converges to 0 or converges to 1 as you choose the event. So limit n tends to infinity, if I use probability of something, let me say that equals 1. So be careful. How many convergence of sequences to 1 does this theorem involves? Uncountably infinite, because for every epsilon positive, you have different sequence. But these different sequences all converges to 1, where you choose what? The event that m sub n minus mu sub x less than epsilon. Okay? So see that this is a number parameterized by n and epsilon, right? So for each epsilon, you have what? A sequence of probabilities. Right? So this is the one of the famous weak law of large numbers. Here, interestingly, the condition is much relaxed. Let me remind you, in this version of strong law, we needed IIDness, second, existence of common mu, and the existence of common variance. What about this weak law of large numbers? IIDness is too strong. We just need what? Uncorrelatedness, especially pairwise uncorrelatedness. Which means that if you choose two of the elements in this, two of the random variables xi and xj, if I is different from j, they are uncorrelated. Second, what about the mean? We assume that they have common mean. Third, they have the common variance. Right? So the first condition is different in these two strong law of large number and the weak law of large number. But as I emphasize, there are many different versions of strong law of large numbers and weak law of large numbers. Now, we are going to prove this one because it's much easier to prove. So, which one? From what do you want to start? You want to start from this one. Got it? Or equivalently, for every epsilon positive, you want to consider the complementary event to this event. That is what? The difference between the arithmetic mean and statistical mean is greater than epsilon. Got it? They are the same. Sorry, We need equality here. If we had strict equality, then here we need equality because it's a complementary event. So we start from this one. Mn minus mu x greater than or equal to epsilon. And the trick is always what? Replace the event with completely equivalent event. And if you plug this definition in, you can easily show that this is simply 1 over n sigma xi minus common mean I from 1 to n greater than epsilon. Now, we've seen something similar to this. What is that? This is the probability of positive random variables right tail probability. And we've learned the Markov inequality, the Chebyshev inequality, and the Chernoff inequality to bound this probability. And let's use Chebyshev inequality, which requires the existence of the second order moment. Here, we assume not only the existence of the first order, we assume the second order. So that's why we use not the Markov inequality, but the stronger version, the Chebyshev inequality. However, when you want to show the convergence in probability, for example, like this, sometimes even though your existence of the second order moment guaranteed, but you'd better just simply use the Markov inequality. I myself also once done that when I was writing one of the papers. Anyway, so what is this one? So remember that suppose you have some random variable, then what? This is, I'd better not say this. Yeah, let me just simply do that. So it's like, even if x is not positive, this event is smaller than that event. So the probability is upper bounded. And then you apply the Markov inequality to that one to have something like this, right? Similarly here, we square this one, right? So here we have epsilon square, and we take the expectation of this squared. What is that? And you can easily show that due to the pairwise uncorrelatedness condition, this is what? The numerator is simply 1 over n squared n times sigma squared. Then what do you have? You have sigma x squared and n epsilon squared. Now let's see, for every epsilon positive, the epsilon square dividing the sigma x squared is fixed. So for each epsilon positive, what happens? As you increase n, this goes to 0. So we establish what? The convergence in probability. So we can claim that this arithmetic mean converges to the common statistical mean in probability. Got it? And here, the reason here, let me show why I said that in the proof of weak law of large numbers, we use the mean square convergence. See this. In both strong law of large numbers and the weak law of large numbers, you remember this one. In most of the cases, almost sure convergence does not imply the convergence in the second mean. However, under these conditions for the strong law of large numbers, this IID and existence, actually, this implies the convergence in the second mean. And let me show you. And also, the this convergence in probability can be implied from the convergence in the second mean as usual, right? So it's worth to prove this. The limit in the mean of the arithmetic average equals mu sub x. Now let's see. So we are interested in this one, the m sub n minus common mean. And as we did, we can have the same trick. So because mu sub x equals n mu sub x divided by n, so this can be written in that form. Okay, so we have the same thing again. And this one is what? Due to the uncorrelatedness, because independence implies uncorrelatedness, we have what? 1 over n squared times n sigma squared. So we have sigma squared over n, which goes to 0 as n tends to infinity. So in these two special strong law and weak law of large numbers, actually, we both we can prove both of the conditions imply the convergence in the second mean, the mean square convergence of the arithmetic mean. Anyway, so we've done two of them, and let's delve more on the central limit theorem. And what's the difference between the law of large numbers and the central limit theorem in this form? Anybody remembers? Yeah. We need to subtract the mean first. And then even I asked you to standardize each term. And sum of each standardized term and divide not by n, but by square root of n. That's what I suggested. So here we have, this is what? This is the z sub I. Let me see. This is not good because we have z and z. So let me say y sub I. That is the standardized version of x sub I. And then we sum up. But we are not interested in the arithmetic mean of y sub I. We have a little bit strangely interested in 1 over square root of n. Got it? So what you want to prove is that this G sub n sequence converges to not a number or deterministic random variable. See that? In the weak law and strong law, the sequence of random variables converges to the spatial random variable. That is a constant, right? But here, we want to show that G sub n converges to what? The standard Gaussian. So we want to prove the characteristic function converges to the Gaussian characteristic function. Now, here goes the most important thing you remember. And then what we are going to do. For example, still we want to talk about the arithmetic mean, for example. See that? What's the implication of the central limit theorem for the arithmetic mean? Here, what we say is this one. So what you do is that we convert this one like this. So 1 over x sub I equals what? The first thing is that we may add and subtract the mean if this confuses you, let me just use 1/n, right? So your arithmetic mean of random variable x's can be viewed of what? The arithmetic mean of the centralized version of x's plus the mean, right? And what about this one? That term can be viewed in this way. Got it? So if you rewrite the arithmetic mean in the form of that strange standardized mean, if you want, standardized version, then it is what? This term scaled by sigma x, the standard deviation of the common standard deviation of random variables divided by square root n plus the common mean. Now, what is the implication of the central limit theorem? The central limit theorem says that this is very close to, right, for sufficiently large n, this is very close to the standard Gaussian. Now, what if you scale the standard Gaussian by multiplying sigma x divided by square root n? This is very close to normal with zero mean and variance sigma x squared divided by n. Now you add mu sub x. What happens? Then you may claim that this entire arithmetic mean is very close the normal with mean mu sub x and variance sigma square divided by n. Here, be careful. If you just let n tends to infinity, what happens? This goes to degenerate Gaussian with zero variance, which is a constant. And actually, that is related to what? Law of large numbers. So this combination of central limit theorem with the law of large numbers says that under mild condition, we have the law of large numbers, but at each large number, our deviation from the constant may be what? A Gaussian. See that? This is our target, and this is our deviation from the target. And that is very close to what? A Gaussian with very small variance and zero mean. Got it? So in the law of large numbers, our error becomes smaller and smaller. But if we do not ignore that one, that is very close to Gaussian noise. Got it? So you see the difference. Now, here goes the simplest example that use one of the famous version of the central limit theorem to prove the Gaussianity. So suppose we have -1 and +1 with probability 1/2, and you sum up n of them. And it seems this is something we've already seen. Yeah, exactly. And you can show by using these steps that this random variable converges to Gaussian, zero mean and unit variance. Got it? And there are some tricks like this. First, you compute the common characteristic function scaled by this 1 over square root n, and then you use the sum of IID random variables results in the characteristic function that is the product of individual characteristic functions. So you have the same characteristic function raised to the power of n. And then you want to let n tends to infinity, but here goes another trick you need to remember. Instead of just taking the limit, you take the logarithmic function first, and then take the limit. And as you remember from high school and calculus, if you have a continuous function, then what happens if you have a continuous function? If f is continuous, what does that mean? And what's the implication of continuity? Amazingly, continuity is related to this one. And you may say that the right-hand side is a stupid notation because this is what? Always x0. But I prefer that one. In your high school math, this was the definition of the function's continuity at the point x0. However, that does not give you much information. What is important is actually this one. So what does this mean? Continuity of f at x0 means that your limit operation can move inside the argument. And vice versa, your limit operation can be taken out of the function operation. That is amazing, right? When you just learned about the continuity, it was so obvious because your high school math appealed to your intuition. But your calculus and analysis course just says that, hey, actually, continuity does not mean that simple thing. Continuity means something absurd. So continuity is a very strong condition. You can switch the order of function evaluation and the limit operation. It's amazing, got it? But one of the important examples is that if f is continuous, right? No, so let me just say that. So this is continuity. And now what is useful is not actually this one, but different thing like this. So suppose we want to prove something like this. Limit x tends to x0 of g of x. So you want to show that this equals some g0. But instead, you take some function of this one and want to show that one. Let me say this is y. Is it okay? You are given to prove this one, but you think about that one. Is it okay? Can you just say this? Somebody asked you to prove that limit, but instead you prove that one. Is it okay? As far as f is continuous function, for example, around here or around the value of that one, it's okay. Why? Continuity means that this can be, sorry, something's not correct. So instead, you prove that one and saying that I've taken a continuous function and showed instead of this one, that one. Why this is just right? Because of the definition. Now this composition can be written as what? The left-hand side is simply limit x tends to x0, f of g of x. Due to the continuity of f, what can you do? Limit x 0. Right? And if, what happens? If not only f is continuous, but also invertible, then what happens? Something like this. Got it? So the trick is that you take the logarithmic function that is continuous and invertible for all positive value. Got it? So here when n is sufficiently, let me see. Yeah. Got it. Yeah. Probably you need to limit omega, but anyway. So you have this form, and if you take the limit, then you can use that famous limit saying that this sequence of numbers that converges to 1 when it is raised to the power of n converges not to 1 but to E, the Euler's constant or Napier's number, 2.7181, something like that. Seven 2.71828. Okay, anyway, so you can show the Gaussianity, approximate Gaussianity of this number. Now, let me go back to the DSCDMA case. In direct sequence CDMA, especially in order to make everything simple, we consider synchronous and a real baseband. Then our observation y can be written simply as this one. Our desired bit, let me say B0, plus sum 1 over n plus k from 1 to capital K. Just a second, just a second. Yeah. And I sub k. Am I correct? Yeah. And each I sub k is IID, and they are shifted and scaled version of a binomial random variable. So it's like the probability of event that I sub k equals n or negative n is 1/2 raised to the power of n. And then you have increasing probability masses, and the distance is 2. Got it? So for example, if n is 36, you start from negative 36, negative 34, 32, blah, 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 and positive 32. Got it? And then you have noise, Gaussian. And we want to establish something like this. Probability of bit error. That is defined as probability of 1 over n sigma ik plus noise greater than positive. Yeah, you can show that when B0 is 1 with probability half and negative 1 with probability 1/2. Okay, so that probability, sorry, greater than 1. Yeah. And you can approximate this one. Something like this. Is it? Let me see. No, this is not true. 1. Yeah. So many people approximate this probability using the Gaussian Q function. So from the beginning, you realize that, okay, some central limit theorem is invoked. So what is done? Actually, not the entire term, but this term. This term is approximated as Gaussian. Something like that, after proper scaling. And then, what is the good approximation to this term? Gaussian with zero mean and variance capital K divided by N. That's why you have that term. So this Gaussian has variance sigma square, and that Gaussian approximated term has variance K divided by N square. Got it? So this is not exactly the central limit theorem. The central limit theorem is invoked to show that this term can be well written as 1 over square root n times Gaussian random variable. Got it? So you didn't show the convergence of this distribution to that distribution. You didn't show that. Because if n tends to infinity, then, if n and k tends to infinity at the same time with n over k fixed, this goes to 0. Got it? Because variance is 1 over n. Okay. Let me see. If k is fixed, I'm sorry. Yeah, if k is fixed and n tends to infinity, then that value goes to 0. Anyway, so be careful. Now, we talk about the Poisson approximation to binomial because it confuses you a lot. I said that it's not the central limit theorem, okay? Even though we have sum of binomials, how do we normalize the parameters gives different limit. If we have NP fixed, then it tends to Poisson random variable. If we don't have that one, then we have Gaussian approximation. Now, before we prove the central limit theorem, one of the central limit theorem, we want to mention this important thing. Sometimes the central limit theorem can be generalized to just independent random variables with same mean 0 and the same variance sigma, but not the identicality, okay? So identical condition sometimes is not required. However, in most of the cases, this is true. They may have unequal distribution, but none of one random variable must dominate when they are summed. Okay? So here, no one random variable dominates. Okay? Here, even variances and means are relaxed, not as identical numbers, right? There are many different versions, right? So whenever you want some Gaussian approximation, search for mathematical journals. And you may find a theorem, a PhD thesis, showing the showing the central limit theorem you need. Got it? Anyway, however, equal distribution case is most simplest one, but actually, I've little bit generalized our proof by allowing different distributions but common mean and variance. Got it? So here goes the starting point. First, we start from the normalized, standardized sum. Okay, so we start from the standardized sum, which means that we have subtracted common mean and we have divided with common standard deviation, but we have square root n here. Now, what is this one? Due to the independence, we have the product of random variables, that is random variable of z, let's say that this is z, divided by square root n. So we find the characteristic function of z sub I, which may be different for each I, but we evaluate at omega divided by square root n. Now, what we do is that we carefully look at this characteristic function and use Taylor series. Because n is large enough, our argument as a real number is very close to 0. So actually, we rely on the Maclaurin series of the exponential function, which is what? 1 plus x squared divided by 2, something like that, where x is j omega divided by square root n. So we have the first term 1, second term j omega z sub I divided by square root n, and third term negative omega squared z sub I squared divided by 2n plus the remainder. And this remainder actually depends on I. So unlike our textbook, we may need one more parameter, r sub ni divided by n. And as n tends to infinity, what happens? This goes to 0. So we are going to drop the term with parameter greater than n. And interestingly, as far as mean and variances are the same, what do we have? In this case, mean is 0. We have the same second order approximation for different characteristic functions under the assumption what? The same mean and variance, so that no one random variable dominates. Actually, they have same variance and same mean 0. And then we have the same procedure as our textbook. So our log of the characteristic function can be written in this form and converges to what? Negative omega squared divided by 2. So we take the inverse function of the logarithmic function, which is exponential, to have what? The characteristic function has limit, that is e to the negative omega squared divided by 2, which is the characteristic function of the standard Gaussian random variable. This is the proof of the central limit theorem. So this figure shows the uniform random variable summed twice, 3 times, something like that. And you can see that after proper normalization, we have the PDF looking very similar to Gaussian. Even just the 3 terms gives us very good bell-shaped curve, but not yet good at here. Anyway. Now the last topic. It seems that I cannot finish this chapter this week, but anyway, in order to be prepared to understand the Borel-Cantelli lemma, we need some definitions learned in analysis. The first one is this notation. See that? What is this one? This is simple union of finite sets. And this looks very similar to the summation notation, so you can easily understand. Second, we have a finite intersection, finite union, finite intersection. And we have now expanded it to countable. See that? Now we have countably infinite number of sets. So this is countable intersection. And we have countable union and countable intersection. And here, interesting thing happens. If you use the, not the tabular method, but the rule method to describe the set, this set, you can write this way. This set is the set of X in the universal set implied such that what? If X is a member of this countable union means that at least one index n you must be able to find. So A is a member of A sub n for some n. For the countable intersection, if X is the member of this set, X must be the element member of every set, right? So you have for all, okay? Here goes for all and there exists. This is interesting stuff. And what do we need this? Because we want to talk about the probability of some event equals 1, where this event involves what? Limit of something. Got it? As I told you, the Borel-Cantelli lemma finds its usefulness in proving almost sure convergence. And almost sure convergence always has in this form. Probability of some event that involves the limit operation equals 1. But you know that this is an event which is a set. So we need to be able to handle a sequence of subsets of the sample space, which means that the sequence of events we need to handle. So not just this A sub i's are subsets, but understood as events, right? So finite union or a finite union of events, a finite intersection of events, a countable union of events, a countable intersection of events, you must interpret that. And then we have something very, very good in our analysis. Here goes the sequence of real numbers. And here goes the sequence of events. The first thing is that given a sequence of real numbers, it may converge or not. That's what our high school students know. But as you take some math courses, they talk about more than just convergence sequences. Sometimes they talk about the cases where subsequence is convergence. But that is not applicable to every case. So what is important is something like this. X sub I plus 1 is less than or equal to X sub I for all I. What does that mean? The next value, next term is smaller than the previous one. And this is called decreasing sequence. And the exact opposite is what? The next term is greater than or equal to the current term. That is increasing sequence. And there is an important theorem by Weierstrass saying that given real sequences, monotonically increasing or just increasing. So increasing bounded sequence, what happens? The limit always exists. Decreasing bounded sequence of real numbers, even though they are not strictly decreasing, the limit exists. So we have good theorem. So we want to have a counterpart. Something like that, or something like that. But we don't have subset inequality. We always have inclusion. So motivated from that one, we want to say that, what if? This inclusion and that inclusion. By the way, in the set inclusion, I prefer using this include proper include subset, something like that. Anyway, so in this case, what happens? The next subset or event is smaller, right? In this case, next subset is bigger than the previous one. And now think about some increasing sequence of increasing subsets. Also consider sequence of decreasing sequence. Can we have the parallels to the Weierstrass theorems to sequence of real numbers? And this motivates us to define what? Limit infimum and limit supremum. So limit inferior, limit superior. So given a sequence of numbers, let me give you an interesting inequality. Consider supremum of xi for all I and infimum of xi for all I. So you have a sequence of real numbers and you know what is maximum, right? However, maximum may not exist. For example, you have a sequence 1 minus 1 over n. What happens? It increases and converges to 1, but 1 is never achieved. So instead of using max and mean, we sometimes love supremum and infimum. That can be replaced by max and mean. And also, you may always say that by including plus and minus infinity, you may always say that they exist, right? So this could be positive infinity and this could be negative infinity, but anyway, they always exist. And interesting thing is this one. If you properly define an increasing sequence and decreasing sequence, you have this relation. So here are two things, lim sup and lim inf. What are they? Simply put, lim sup is what? Lim sup is the limit of supremum sequence. Then what is the supremum sequence? So consider this one. Suppose you have a sequence. Just take sample. And then lim sup is what? First, you construct the sequence of supremums by doing this. First, you consider supremum of everything. And that is this one, right? And then for the first term, you remove the first term, and then from all these sequence terms, you take the supremum and supremum. What happens? Your supremum always decreasing. So you have a sequence of decreasing numbers. And if this entire, since that entire sequence is bounded by negative infinity, what happens? This always exists. Now consider the same thing. First, you consider infimum of every term. And then for the second term, you remove the first term and consider the infimum. What happens? Your infimum sequence monotonically increasing. Now you have monotonically increasing sequence of real numbers. What happens? It always converges. Now the question, what happens? What about this and that one? You always can establish this inequality, right? Because the first term is the biggest one and equals to the left one. Here, the first term is the smallest one. That is the rightmost one, right? Sorry. The first one is the biggest one and same as this one, right? The first one, first one is smallest one and that is equal to that one, okay? So you have this equality and that equality. What about this one? What about this one? This is the kind of minimum of maximum, and that is maximum of minimum. You can always show this inequality. Now, same thing happens for the sequence of sets. And in order to do that, consider this. What is the corresponding thing to suprema? The biggest one. Yes, countable union of all the events. So here you have union of all events. And intersection of all events. And you want to have inclusion inequality. But as I told you in the set, you don't need this one. And here goes the set lim_sup and set lim_inf, which can be written is this one. This may be confusing, but
Dr. Joe, it is time to wrap up.
let me remember something like this. So this is termed as lim_sup, and this is termed as lim_inf. And this notation is motivated by what? These things. And similarly, what is this one? This one is what? When you have a sequence of events, you cut at the mth time index, and you take the union of everything. Now, what about this sequence? This sequence always decreases. What about that one? This sequence, you take the intersection from mth term to infinity. And this sequence always increasing. And you can also show that when this I equals 1, they are the same. When I equals 1, they are the same. So you can easily establish something similar to that. But this is so far for the measure theory. What about the probability theory? Here goes the probability theory part. So you take the probability of these things. Then you have the scalar inequality back, right? Why do we have this one? From the countable additivity property of our measure, probability measure. If you have an event bigger than the other event, the probability of that event is always greater than or equal to probability of that event. So we have this one. Got it? And now you may say that, okay, then what happens? Here goes the thing. If we have an increasing sequence of events, so in this case, the limit of the probability sequence converges, right? And this exists. And also, in increasing sequence, the limit exists, okay? And the limit is same as what? Same as that one. And why this happens? In order for the limit exists here, the lim_sup and lim_inf must be the same. In order for here, this probability to be equal, if these two are equal, then these probabilities are equal, and the limit exists. And interestingly, you can easily show that if we have increasing or decreasing sequence, they are the same. They are the same. Got it? So this is what is really needed to understand the Borel-Cantelli lemma. And these are definitions. And as you see, countable intersection and lim_inf, lim_sup, and countable union. By the way, probably I need this thing. That is just to, I believe that is decoration. It doesn't matter. But anyway, people love to put n tends to infinity. So here goes some examples where you can practice your skill. So given this sequence of events, you may find whether this sequence converges or not. And given this sequence of events, you may find this sequence converges or not. And here goes some exercise problems you want to tackle. And then next time on this Thursday, I will talk about the Borel-Cantelli lemma. But in order to understand that one, you may have to understand this one. So what is the complement of this event, by the way? What is the complementary event of lim_inf? Interestingly, you can show this. So this is lim_inf of the sequence, which equals lim_sup of the complementary events. Okay. And this is very simple, actually. You've learned this already from the de Moivre's theorem, something like that. Union of A complement equals intersection of A complements. And intersection of B complements equals union of B complements. And now you mix up. So replace as this one, and then combine, you have that one, even if you have countable union and intersections. Same thing, got it? So as you see, here goes lim_sup of events. And that is what? That is an event. And here goes the lim_inf of the complementary events. And you may easily see that, hey, this is same as that one because you complemented the event. So you have probability 1 and you have lim_inf of the sequence, right? And this is required what? In our proof of almost sure convergence. See that? Suppose you have constructed a decreasing sequence or increasing sequence. Then this is nothing but the limit of an event of sequence, a sequence of events. And that probability equals 1. So we can establish a strong law of large numbers, an almost sure convergence, something like that. Anyway, we will cover this next time. That's all for the